Welcome to the video help with physics problems for Physics 1A. In this video, we're going to cover homework set 6, part 2. That's everything under the heading sound wave. For 1121 students, this is questions 6 to 11, and for 1131 students, it's questions 7 to 14. Problem 6 for 1121 or 7 for 1131. In this question, we're asked to calculate the energy density at a certain distance from a siren. Here's our siren. It has a power output of 47.5 kilowatts. It radiates that into space, so around the surface of a sphere. And we're investigating the intensity at a distance of 4.82 kilometers. We're told that the speed of sound is 343 meters per second. And we're asked, what's the energy density? Well, energy density is just the energy over the volume, which is the power in a certain amount of time over the volume. So we can write this as the power over the surface area times the length in which the wave is traveling, so let's just call that Z, over time. Just putting this time down the bottom here. Now this is the velocity of this wave here. So we can write that this is P over the surface area times the velocity of the wave. Okay, so now all we need to do is substitute in the power. We're told is 47.5 times 10 to the 3 watts. The surface area, this is a sphere, so it's 4 pi times r squared, so that's 4.82 times 10 to the 3 squared, and then times the velocity, which is 343. So then all we need to do is solve this on the calculator. When you do that, you get 4.74 times 10 to the minus 7, and this will be joules per meter cubed. Or we can write it as 474 nanojoules per meter cubed. And that's the answer to that problem. Problem 8, which is for 1131 only. In this question, we have a source and we have a detector. There's two ways for waves to travel from the source to the detector. They can go directly, covering a distance d, or they can go up to a layer of atmosphere, which is a height capital H, above the source and the detector, and be reflected back down. When this happens, we get constructive interference. So let's call this one path 1. So path 1 and D give constructive interference. However, this layer of atmosphere can move up a little bit, and if it moves up a distance little h, and the wave goes from the source to this new height of atmosphere and back down, let's call that path 2, we get destructive interference, and we're told that there's no other maximums or minimums in between. So path 2 and D give destructive interference. So we know that the difference between path 1 and path 2 is equal to lambda on 2. We know that because the path difference between D and path 1 is equal to n lambda, where n is any integer, and then the path difference between path 2 and D is n plus a half lambda, where it's the same n. So lambda over 2 is equal to the length of path 2 minus path 1. So now to work out lambda, we can just substitute into this equation. Now in path 2 it has to go up and back, and we can use Pythagoras' theorem. The height is h plus h, the length along here is d over 2, to work out that distance. So lambda is equal to this 2, so 2 times path 2, which is the square root of d over 2 squared plus h squared minus path 1. And there's 2 times this because it has to go up and then it has to go back, which is 2 times the square root of d over 2 squared plus, in this case it's just going the height h, so this is h squared. Okay, so let's just put this 2 inside to get rid of this. So we've got 2 times the square root of d squared plus 4h plus h squared. When the 2 goes inside the square root sign, it becomes a 4, minus the square root of d squared plus 4h squared. And that's our answer for lambda. Okay, this is problem 7 for 1121 or problem 9 for 1131. In this problem, we're given the pressure of 2 waves travelling through space. P1 is equal to P sine 2 pi ft, and P2 is equal to P sine 2 pi ft minus 2 pi phi. And we're asked what's the amplitude of the resultant wave. Well, the first step is to work out what the resultant wave is. So to get the resultant, we just need to add these two together. P1 plus P2 is equal to P, that's a common factor, sine 2 pi ft plus sine 2 pi ft minus 2 pi phi. So to add these two together, we're going to need to use the rule sine A plus sine B is equal to 2 sine A plus B on 2 cos A minus B over 2. So this is A, this is B. Substituting in, we end up with P1 plus P2. We've got a P out the front, so we've still got that, but we've also got a 2. It's 2P sine. Now 2 pi ft plus 2 pi ft gives us 4 pi ft on 2, so that's 2 pi ft. And then we've got minus 2 pi phi on 2, so that's minus pi phi. And then we've got cos of 2 pi ft minus 2 pi ft, they cancel out, and we're left with this 2 pi minus 2 pi phi on 2, so that's pi phi. Okay, so this part here is just our wave expression, and the 2p cos pi phi gives us the amplitude. So we've got 2p cos pi phi sine 2 pi ft minus pi phi. Okay, so what we need to do now is evaluate this amplitude at the values of phi we're given. So amplitude is equal to 2p cos pi phi. So when phi is equal to 0, we've got 2p cos of 0, and cos of 0 is 1, so this is equal to 2p. When phi is equal to 1/4, we've got 2p cos of pi on 4. Now remembering our little equilateral triangle with pi on 4, 1, 1 root 2, cos of pi on 4 is 1 on root 2. So this is equal to 2p over root 2. So that is equal to root 2p, or if you want to evaluate it on the calculator, you can write it as 1.41p. Then we're asked if phi is equal to 1/6, in which case we have 2p cos pi on 6. So we remember our other little triangle. We've got 1, we've got 2, so this side's root 3, this is pi on 3, and this in here is pi on 6. So we've got 2p. Now cos of pi on 6 is adjacent over hypotenuse, so that's root 3 on 2. So we've got root 3p, and if you evaluate that on your calculator, you end up with 1.73p. And then finally we're asked if phi is equal to 1/8, in which case we've got 2p cos pi on 8. Unfortunately, there's no nice analytic way to solve this, so you just need to solve it on your calculator. When you substitute in, you end up with 1.85p as the solution to this one. Problem 8 for 1121 or 10 for 1131. In this one, we have a note with a frequency of 300 Hertz and an intensity of 1.0 microwatts per meter squared. And we're asked what's the amplitude of the vibrations in the air particles. Okay, so this is a sound wave, so the amplitude is in the direction of motion of the wave, and we usually give it the symbol S max. So we need a couple of equations to solve this one. We have shown that the power is equal to a half rho, the density of the medium, times the velocity, omega squared, times the area, times S max squared, the amplitude squared. And we also need to make use of the intensity is equal to the power over the area. This is the power here. Okay, so rearranging this one, we've got S max squared is equal to 2 times the power over rho v omega squared A. So this is 2 over rho v omega squared. Now power over area is equal to the intensity, so times the intensity. So now what we can do is we can substitute numbers in. We've got 2. We're told the intensity here is 1.0 times 10 to the minus 6. Now the density of air is 1.21 kilograms per meter cubed. So we can put that in here. That's at around 20 degrees C. The velocity of sound in air is 343 meters per second. Omega squared, omega is equal to 2 pi f, so that's 2 pi times 300 all squared, and that's everything substituted in. So we can solve that on the calculator and we get 1.36 times 10 to the minus 15. Now this is S max squared, so to get S max, the amplitude of the vibrations, we need to take the square root of that. When we do that, we get 3.7 times 10 to the minus 8 meters. And that's the answer to this problem. Problem 9 for 1121 or 11 for 1131. In this one, we're told that the sound level is increased by an additional 30 decibels. So we can write the final sound level is equal to the initial sound level plus 30 decibels. Now in part A, we're asked show that its intensity increases by a factor of 1000. So we need to use our formula for sound levels and intensities. The sound level is equal to 10 times log to the base 10, the intensity over some reference intensity I0. So substituting this into this equation here, we have 10 log to the base 10 IF over I0, the final intensity, over the reference intensity, 10 log to the base 10, the initial intensity over the reference intensity, plus 30. Okay, now expanding this log, when we do a division within a log, we can subtract the total log functions from each other, Let's just divide everything through by 10, so this becomes 3. So we've got log to the base 10 IF minus log to the base 10 I naught is equal to log to the base 10, the initial intensity, minus log to the base 10, the reference intensity, this is 3 now, so 3. Okay, now the reference intensity, the log of that cancels out, and we end up with log to the base 10. We subtract this one from this one, so we have the final intensity over the initial intensity is equal to 3. Now to get rid of the log function, if we do 10 to the power of both sides, then we've got IF over II is equal to 10 to the power of 3, which is 1000, which tells us that our final intensity, IF, is equal to 1000 times our initial intensity. Now in part B, we're asked to show that its pressure amplitude increases by a factor of 32. Well, the intensity is equal to the pressure amplitude squared over 2 rho V. So the important point is that it's proportional to the pressure amplitude squared. So that tells us that IF over II is equal to P max F squared over P max I squared, and we know that's equal to 1000. Now if we take the square root of this and of this and of this, we end up with the square root of 1000 is equal to 31.62, is equal to this, which is the pressure amplitude of the final one over the pressure amplitude of the initial one, which tells us that the final pressure amplitude is equal to 32 times the initial pressure amplitude, which is what we were asked to show. Problem 12, which is a 1131 only problem. In this problem, we have two loudspeakers, S1 and S2. S1 emits sound with a frequency of 200 Hertz and a power of 1.2 times 10 to the minus 3 watts. And speaker 2 has a power of 1.8 times 10 to the minus 3 watts, the same frequency. We consider a point P here, which is 3 meters from speaker 2 and 4 meters from speaker 1. And these speakers are vibrating in phase. Okay, and this is sound, so we'll take its velocity through air as 343 meters per second. Now part A, we're asked how are the phases of the two waves arriving at P related? Well, to get the phase difference, we're going to need to know the wavelength. So we know V is equal to F lambda, so lambda is equal to V on F, which is 343 over 200, which is equal to 1.715 meters. Now the other thing we need to know to get the phase difference is the path difference. This is just the 4 meters minus the 3 meters, which gives us the 1 meter. And so the phase difference is equal to 2 pi times the path difference over lambda. So this is 2 pi times 1 over 1.715. And when we solve that on the calculator, we get 3.7 radians. It's the difference when they arrive at P. Okay, now part B says what is the intensity of sound at P if S1 is turned off? So all the sounds coming from S2. Well, intensity is equal to power over area, and the power is spreading out from this speaker across a spherical surface. So the power is 1.8 times 10 to the minus 3. The surface area of the sphere at P, it's got a radius of 3. So this is 4 pi r squared, or 4 pi 3 squared in this case. And so that is equal to 1.6 times 10 to the minus 5 watts per meter squared. Part C, we're now asked what is the intensity if speaker 2 is turned off and it's just due to speaker 1. Well, we use the same equation. The power coming from speaker 1 is 1.2 times 10 to the minus 3, and this is spread out over a larger surface area as the radius is now 4. And so we've got 4 pi times 4 squared down here. Now solving that on the calculator, you end up with 6.0 times 10 to the minus 6 watts per meter squared. Finally, in part D, describe qualitatively how the intensity at P with S1 and S2 would compare with the sum of your answers to B and C. Okay, well, if these were perfectly in phase at P, all we'd have to do was sum these two to get the total power. But as they're not in phase, we're going to have a lower intensity as there's going to be a bit of destructive interference. So it will be lower as there is interference. Okay, so it's lower because the interference isn't completely constructive. There's a bit of destructive interference there because of this phase difference. Problem 10 for 1121 or 13 for 1131. In this problem, we have a pipe which is open at both ends and it has a length of 0.49 meters. We have a sound source and we can vary the frequency from 1000 Hertz to 2000 Hertz. And we're told in this question that the velocity of sound in air is 339 meters per second. And we're asked, what are the resonant frequencies? In this range here. Okay, so, well, the fundamental frequency will look like that. And so since it's open at both ends, when we have n, lambda over 2, is equal to the length of the pipe, we're going to have a resonant frequency, so resonance, where n is an integer. Okay, so we know the velocity, we know the frequencies, so let's get rid of this lambda. We have v is equal to f lambda, which tells us lambda is equal to v over f. We can put that into this equation, and we end up with nv over 2f is equal to L. Now what we're interested in is these frequencies, so let's make frequency the subject. So frequency is equal to nv over 2L, or that's n, any integer, times 339 over 2 times 0.49. Solving that on the calculator, we end up with n times 345.9 will give us the resonant frequencies. So the first one will be 345 Hertz, which is obviously too low. Second one is also too low. When we get up to n equals 3, we've entered this region. So when n equals 3, then we have the frequency is equal to 1038. When n is equal to 4, we have that the frequency is equal to 1384. And when n is equal to 5, we have that the frequency is equal to 1730. And then when n equals 6, we're above 2000, so we're out of this range. Part B says sketch the displacement modes for each, ignoring the end effects. So in B, we've got, in this first one where n equals 3, we've got 3 half wavelengths. So there's 1, 2, 3 there, so that's what this one looks like. In this next one, we've got 4 half wavelengths. So we've got 1, 2, 3, 4, and in this final one we've got 5 half wavelengths. So it looks like that. There's 1, 2, 3, 4, 5 half wavelengths there.
Now part C says explain what end effects are and how they would change your results in the real case. So end effects are little things which happen at the end of the pipe. It actually causes the antinode to be slightly outside the pipe. So that's going to cause our wavelengths to be slightly longer. Now, if our wavelength is slightly longer than it was before, it means that the frequency has to be slightly smaller than it was before. So these end effects will decrease the frequency a bit. The end effects are relatively constant over a wide range of frequencies.
Problem 11 for 1121 or 14 for 1131. In this problem, we've got a tuning fork. We've got 2 tuning forks. One has a frequency of 384 Hertz, and one has some unknown frequency. And we're told that the beat frequency is equal to 3 Hertz. And we're told then we put a lump of plasticine on this one, and then the beat frequency decreases, and the frequency of this tuning fork, let's call that frequency T for tuning fork, also decreases when we put the lump of plasticine on it. And we're asked, what is the frequency of this tuning fork equal to? Now we know that the beat frequency is equal to the difference between the 2 tuning forks. So it's 384 minus FT, or if this tuning fork has a larger frequency, it will be FT minus 384. And this is 3. Let's call this case 1 and this case 2. Now in case 1, where the frequency of the tuning fork is less than the 384 Hertz, if we decrease the frequency of the tuning fork, this number is actually going to increase. So that can't be the case. So let's consider case 2. Now in this case, if we decrease the frequency of this tuning fork, then these 2 numbers are going to get closer to each other, and so the beat frequency will decrease, which is what we observe. So this is the case that we need to use here. So we have 3 is equal to the frequency of the tuning fork minus 384. So the frequency of the tuning fork is equal to 384 plus 3, which is 387 Hertz.